Hi there. In this session, we're going to be going through the process of how you can assign an elemental formula to a peak in a mass spectrum based mainly on the accurate mass. And we're going to solve this problem in 3 steps. The first step is a clever algorithm that generates all possible chemical formulae that could be matched to a peak of interest. The second step then will be to cut that list down to chemically plausible formulae using a simple set of rules. And then in the third and final step, I'll explain how we can use the isotopic distribution to focus in, hopefully, on just a single formula. So in this video, I'll be going through all the background explanations of the algorithms and the methods. And then there'll be a second video where I'll walk you through the process in Excel to demonstrate all these methods in action. In practice though, when would you actually need to be able to do this? Accurate mass assignment is the process you'll use whenever you want to identify unknown or unexpected peaks in your mass spectra based on their accurate mass. So examples of when this might come in handy would be when you're trying to identify an unexpected contaminant or byproduct in a pharmaceutical sample, or maybe when you're surveying metabolites, or also when you're analysing environmental samples. In all these cases, there could be a huge number of peaks you need to identify, and there's no way you'd be able to buy standards for all of them. So attempting to assign those peaks using their accurate masses may be the only potential strategy open to you. But this strategy will only work if you're using an accurate mass spectrometer. So what is an accurate mass spectrometer anyway? Well, quite simply, an accurate mass spectrometer is an instrument capable of measuring the masses of ions sufficiently accurately that you're able to determine or limit the possibilities for elemental formulae of those ions. And this normally means having an instrument that's capable of providing you with both high mass accuracy and high resolution. So you'd normally want to be using an instrument which would be specified with at least 5 ppm mass accuracy in order to be able to attempt this process. It will work on instruments with lower mass accuracies, but with less assurance of success unless you're only working on very small molecules or you can already cut down some of the possibilities of the assignments using information you know about that sample. And you'll see that I've added a link to a paper that gives useful definitions of terminology associated with accurate mass spectrometry onto the slide here, and I strongly recommend reading it. The other thing it's worth discussing at this point is that if you're going to be undertaking this task regularly, you'd normally be relying on a software package to help you do it. However, these software packages work by different methods, and in some cases they rely on databases that you may not have access to. In other cases, when the results are very important, it may be vital to check the calculations manually to make sure that you're confident in the assignment. So however you're going to be undertaking the assignment of accurate mass ions in mass spectra in practice, it's important that you understand the process that would be used to assign an elemental formula to that ion. And that's the process we're going to be describing in this video. So here's an example of a complex organic matter mass spectrum that, in this case, contains close to 10,000 peaks that we might want to assign. Now obviously you'd never want to try to assign 10,000 peaks manually, but the process of assigning each one of these individual peaks would use the same approach that we're about to go through, just repeated 10,000 times. And the identical approach is used whether you're looking at fulvic acids in environmental samples or whether you're looking for metabolites or lipids in biomedical samples. So let's start at the beginning. Remember that the masses of each element are not integers, with the exception of carbon, which does happen to weigh exactly 12 daltons. However, all the other elements have a small mass defect associated with them. So hydrogen doesn't weigh 1 dalton, it weighs 1.007825 daltons. And nitrogen doesn't weigh exactly 14 daltons, it weighs 14.003074 daltons. So if we were able to measure the mass of an ion accurately enough, then there would be only one combination of all those fractional masses that would add up to the right mass to be assigned to that ion. But whenever we actually measure the masses of ions in a mass spectrometer, we don't measure them exactly. Instead, we only get an estimate of their mass, which will show some mass error between the measured mass and the true mass. If we can measure the mass error of multiple peaks in the same spectrum, then we can start to get an understanding of the statistical distribution of the mass errors. So as an example, if we go back to this spectrum and went through the process of assigning all the peaks, and then looked at the mass errors associated with all those assignments, we'd get these results. Along the bottom axis of both graphs, we can see the mass errors associated with all the assignments. In this right-hand graph, I've plotted the mass error of each assigned peak against its signal-to-noise ratio. And in the left-hand plot, I'm showing the numbers of assignments in the spectrum that fall within specific mass error ranges. So this plot shows that the mass errors associated with all the assigned peaks in this spectrum fit within a statistical distribution. And this feature is true of all mass spectra. There's always a statistical distribution of the mass errors, and normally that distribution will be so wide that it's quite common that you can't propose a single formula for any individual peak. However, if you know the error range for the mass of a peak, then you can predict all the potential elemental formulae that could be assigned to that peak. But then out of that list of potential elemental formulae, how can you go about choosing the right one to use? Well, luckily there's a logical process that we can use to solve this problem. In the first step, we need to have some method of proposing all the possible ionic formulae for each peak in a spectrum. And then for each one of those peaks, we can narrow down the list of possible assignments to formulae that are chemically plausible by applying some heuristic rules, such as the Kind and Fiehn or Lewis and Senior rules. And then finally, from that narrowed down list, we can try to use the isotopic distribution that we can detect in the mass spectrum to further narrow down the list of possibilities, hopefully reducing it down to just a single assignment. So let's start at the beginning of the process and understand how we can generate a list of all possible chemical formulae within a given mass error of a peak mass. The naive way to approach this problem would be simply to search through every possible combination of all elements that fit within some maximum possible stoichiometries. Let's say, for example, up to 100 carbons, 200 hydrogens, 100 oxygens, 10 nitrogens, and 5 sulfurs. But within these limits, there are actually over 135 million possible combinations that we'd need to search through, all the way from a molecule containing just one carbon and no other atoms, up to a maximum possible of C100, H200, O100, N10, S5. Of course, not all of these combinations are possible chemically, and neither do they all add up to the right correct mass, but we'll come back to that point. The main takeaway from here is that systematically searching through all possible combinations of atoms to identify the formula for any peak isn't a practical proposition. So, is there a better way? Well, of course there is, or this would be a very odd lecture. There are in fact multiple ways of solving this problem, but the one I'm going to be describing here is known as the Dromey Foyster algorithm. It was developed in 1979 by Jeff Dromey and Gordon Foyster at the University of Wollongong in Australia. Jeff Dromey was a professor and Gordon Foyster was actually the master's student in his group, and there can't be many master's projects where the outcome of the project is still being used and discussed over 40 years later. The key parts of the Dromey Foyster algorithm are based on two tricks. The first of these is that because carbon has no mass defect, it weighs exactly 12 daltons, then in any molecule or fragments of molecules, all of the mass defect must come from the other elements. And the second trick is that CH2 weighs almost exactly the same mass as a single nitrogen atom. The easiest way to understand how these two tricks can be used to massively reduce the number of calculations required to assign a formula to any given peak is to do a manual walkthrough of such a calculation. So let's start with the same situation we discussed earlier. So we'll set ourselves a maximum stoichiometric limit of up to 100 carbons, 200 hydrogens, 100 oxygens, 10 nitrogens, and 5 sulfurs. Now when you're searching through any possible range of formulae, the elements with the largest possible stoichiometries occupy the largest proportion of the search volume. In most organic molecules, carbon and hydrogen have by far the largest possible number of values. So if we could discount those from the search space we'd have to iterate through, then this could have a huge benefit on the number of calculations we'd need to perform. In fact, within the stoichiometric limits we've set ourselves, we'd now only have to iterate through about 6,700 possible formulae instead of the previous 135 million. But of course, now we're only iterating through the heteroatoms, so how do we account for the carbons and hydrogens that we're now missing but that we'll need in the final formula? In order to understand how the Dromey Foyster algorithm does this, let's walk through an example as if we're trying to assign a peak in a mass spectrum that comes from brilliant blue. Brilliant blue is a dye that's used in medical processes, food colorants, and for coloring pharmaceutical products. And it has the formula C47, H49, N3O7S2. And that corresponds to a neutral molecular mass of 831.301 daltons. When you're trying to assign formulae to peaks in mass spectra, many of the steps require you to be working with the masses of neutral molecules rather than ions. So this means you need to modify the mass of the peak in the spectrum by the mass associated with however it's been ionized. If the molecule was protonated to create the ion, then you'll have to remove the mass of the added proton before trying to assign the formula. Alternatively, if the ion was formed by deprotonation, then you need to add the mass of that proton back onto the peak mass to predict the original molecular mass. As brilliant blue is an acid, we would normally be analysing it in negative mode in a mass spectrometer. For the purposes of this walkthrough, we'll assume that by chance we've got a peak in our spectrum that corresponds to the exact mass of the deprotonated brilliant blue ion. As we know this is a negative mode spectrum, we also know to add the mass of that proton back onto the peak mass, and we'll refer to this reconstructed molecular mass, as derived from the spectrum, as the spectral mass. Now, in order to assign a formula to this spectral mass, using this first version of the Dromey Foyster algorithm, we only have to iterate systematically through all possible combinations of the heteroatoms. So we can start our imaginary software doing that. For each one of these combinations, all of the following calculations would need to be done. But we'll just look at the example when we're calculating this specific iteration that corresponds to the actual combination of nitrogen, oxygen and sulfur that is actually in brilliant blue. Then, for each iteration, we have to calculate the mass of that heteroatom component. So in this case, that's 3 nitrogens, 7 oxygens and 2 sulfurs, which means that the non-carbon and hydrogen parts of this molecule weigh 217.9 daltons. And the mass difference between this heteroatom component and the spectral mass must be the mass of the parts of the molecules containing only carbon and hydrogen. Because carbon has no mass defect, then all the mass defect in this missing mass part must come from the hydrogens. Remember, that was the first trick in the Dromey Foyster algorithm. We know hydrogen has an exact mass of 1.007825 daltons, meaning that its mass defect is 0.007825. Then, to calculate the number of hydrogens in this residual mass, according to the Dromey Foyster algorithm, we divide the mass defect of this missing mass by the mass defect of hydrogen. And in this example, because the fictional spectral mass happens to be the exact mass of brilliant blue, this fraction gives us the answer of exactly 49. In a normal spectrum, of course, there would be some mass error associated with the spectral mass, therefore this fraction wouldn't give you a nice integer result, so according to the Dromey Foyster algorithm, you actually need to round the number that comes out of this fraction to the nearest integer in order to predict the number of hydrogens. And this trick will work for most small molecules that contain up to around 125 hydrogens. Then, having calculated the number of hydrogens you need to add on to the heteroatom mass you calculated earlier, then you can find the carbon-only residual mass and divide that by 12 to get the number of carbons. Why don't you pause the video here, try that in Excel or on a calculator, and see if you get 47 carbons. So to summarise this first trick in the Dromey Foyster algorithm, you only need to iterate through all possible heteroatom combinations, and then for each one of those you can calculate directly the appropriate numbers of hydrogens and carbons to add to the formula to give an ion of the correct approximate weight. And this approach significantly reduces the number of iterations you have to calculate through for every peak. But Dromey and Foyster actually went one stage better than that and managed to find a way where you can also avoid iterating through the numbers of nitrogens. This second trick in the Dromey Foyster algorithm is based on the fact that CH2 and a nitrogen atom have very similar masses. And it's this that allows us to use a shortcut to calculate the numbers of nitrogens as well as the numbers of carbons and hydrogens when we're doing our iteration. So by this trick, we now only need to iterate through all the possible combinations of oxygen and sulfur in our example. And again, I'll walk through the calculations associated with this correct combination of oxygens and sulfurs, but remembering that we'd have to do the same calculation with all iterations in reality. But for the iteration where we have 7 oxygens and 2 sulfurs, then this part of the molecule weighs 175.9 daltons. And that means that the missing part, that's the difference between the spectral mass and this heteroatom component, is 655.4 daltons, and that must be made up of only carbon, hydrogen, and nitrogen. And now the Dromey Foyster algorithm uses its cunning trick. Because CH2 and nitrogen have very similar masses, it's possible to calculate a nitrogen-free formula that will be very close in mass to the real formula. So the next stage of the calculation now is to work out the formula of this nitrogen-free molecule. We can demonstrate this calculation pretty easily in Excel. So first of all, I'll enter the missing mass, that being the spectral mass minus the heteroatom component, into this top row. And then the next thing to do is to calculate the mass defect of that missing mass, which we can easily do using the round down function in Excel. The next stage is to calculate the mass defect of hydrogen, and so we'll repeat almost the same calculation again. The next step is now to make a guesstimate of the number of hydrogens using the same process that we used in the previous trick of the Dromey Foyster algorithm. So we divide the mass defect of the missing mass by the mass defect of hydrogen. And then we round to the nearest integer. The next stage is to calculate the number of carbons using this guesstimate for the number of hydrogens. So we take the missing mass and subtract from that the mass of now 50 hydrogens. And then we divide that residual mass by 12 to get the number of carbons. And of course we have to round that to the nearest integer. And now we can use that calculated number of carbons to update our guess for the number of hydrogens. And that's a very similar calculation. So we take the missing mass, we subtract from that the mass of carbons, that's 12 times 50, and then we divide that residual mass by the mass of hydrogen to calculate the number of hydrogens. And then, surprise, surprise, we also round that to the nearest integer. And so this series of calculations indicates that the nitrogen-free molecule would contain 50 carbons and 55 hydrogens. So we can produce a complete nitrogen-free formula for this molecule by combining C50 and H55 with the heteroatom iteration. And so that then gives us a total formula of C50, H55, O7, S2, and a molecular mass of 831.3 daltons. Then, to calculate the number of nitrogens that we should have, first of all you have to calculate the mass difference between the mass of the nitrogen-free molecule and the measured mass of the molecule from the spectrum. Then we divide that mass difference by the mass difference between CH2 and nitrogen. As before, because we're using the exact mass of the molecule as the spectral mass here, that gives us the exact answer 3. But in a normal spectrum with a mass error, you'd simply round to the nearest integer at this stage. And then, having calculated the number of nitrogens, then you just revise the formula of the nitrogen-free molecule by subtracting 1 carbon and 2 hydrogens for every nitrogen. So we have to remove 3 carbons from this molecule, which drops us from C50 to C47. And if we have to remove 2 hydrogens for every nitrogen, that means we need to lose 6 hydrogens, which would drop us from 55 down to 49. And as you can see, that ends up producing the correct formula for brilliant blue. And this second one of Dromey and Foyster's tricks works for molecules up to 7 nitrogens. Beyond that, you have to wrap back around again, and you have the option of it being, say, either 1 or 8 nitrogens. So to summarise trick 2 in the Dromey Foyster algorithm, you simply need to iterate through all combinations of elements except for carbon, hydrogen and nitrogen, and then for each one of those heteroatom iterations you can calculate the corresponding numbers of carbons, hydrogens and nitrogens directly. And that means we now only need to iterate through approximately 600 combinations per peak instead of the original 135 million. And as you've just seen, it really does work. But up to this point, we've only walked through the correct iteration that you'd find as one of the possible results in the Dromey Foyster algorithm. So now let's look at the output you'd actually get for our imaginary brilliant blue peak in a mass spectrum, but this time with a small mass error included. Now for this peak, as for every other peak in the mass spectrum, we'd iterate through all possible heteroatom combinations, and then for each one calculate the corresponding carbon, hydrogen and nitrogen stoichiometries. And then, providing those numbers of carbons, hydrogens and nitrogens were still within the stoichiometric limits we'd set ourselves, we could then calculate the resulting ion mass, and then the mass error between that and the peak mass that we'd seen in the spectrum. And then we'd only keep those formula where the mass error was within some specified mass error limit. So if we had a peak mass at 831.28046 Daltons, this is a list of all 251 formula within our stoichiometric limits that are within 10 ppm of that mass. And I've highlighted the correct formula for brilliant blue in this list. But 251 formula is a lot. And that's just for a single peak in a spectrum that could contain hundreds or thousands of other peaks. So then how can we narrow this list of possible formula for each peak down to a more manageable number? And to answer that question, we'll go to the second stage in our 3-stage process. In the first step, we've used the Dromey Foyster algorithm to propose all possible chemical formulae within a given mass error limit of a peak in the mass spectrum. And in this second stage, we're going to use a series of heuristic rules to filter down those possible formulae down to those that are chemically plausible. And the method we're going to be using for this comes from this seminal paper by Kind and Fiehn, and it's one I strongly recommend reading. The first rule listed in the Kind and Fiehn paper is the Lewis or octet rule. According to this rule, when forming compounds, all main group atoms try to gain, lose, or share electrons so that they end up with a stable electron configuration characterized with a full outer s or p shell. In order to test whether any proposed formula passes this Lewis rule, you can use the rings plus double bonds equivalent equation that is normally used to estimate the number of double bonds or rings in a molecule. But it's also the same equation we used way back in the first lecture in this series to test whether an ion in an electron ionization spectrum could be a radical molecular ion. So it's a multi-purpose, very useful formula. As a reminder, to calculate the rings plus double bonds equivalent number for any proposed formula, you take the number of carbons, subtract from that half the number of hydrogens, add on to that half the number of nitrogens, and then add 1. And when doing this calculation, you include any number of tetravalent atoms in with the total number of carbons, all monovalent atoms such as hydrogens in with the hydrogen number, and any trivalent atoms such as phosphorus in with the nitrogen. then if the result is not a whole number, then this proposed molecule doesn't pass the Lewis rule, and you'd reject it from your list of possible formula. There are some molecules that will break this rule and still be valid molecules, and in particular that includes molecules that contain higher valence versions of nitrogen or phosphorus, but it will work for the vast majority of cases. But it is important to make sure you're applying this to the molecular formula and not to the ionic formula. So if the ions you're expecting to see in your spectrum are protonated, then you need to remove that extra proton from the ion formula to reduce it back to the molecular formula. Similarly, if you're working in negative mode and you were expecting a deprotonated ion, then you need to add the missing proton back into the equation before testing to see whether it passes the Lewis rule. The second set of heuristic rules recommended by Kind and Fiehn are the senior rules, and these were first proposed way back in the 1950s by a chemical mathematician called James Senior, hence the name. The senior rules state that the sum of the valences, or the total number of atoms having odd valences, must be even, and that the sum of all the valences must be greater than equal to twice the maximum valence, and thirdly, that the sum of the valences must be greater than or equal to twice the number of atoms minus 1. But that's a lot of information to suddenly absorb, so let's test these rules using glycine as an example, with glycine having the formula C2H5NO2. So in glycine, we have 2 carbons with valence 4, 5 hydrogens with valence 1, 2 oxygens with valence 2, and 1 nitrogen with valence 3. And so the sum of the valences is 20. And of course 20 is an even number, and that means this passes the first of the senior rules. The maximum valence of any of the atoms in this formula is 4 for carbon, and the second senior rule tells us that the sum of the valences must be greater than or equal to twice this maximum valence. So 2 times 4, the maximum valence is 8, and the total valence is 20, and that is greater than the 8 of twice the maximum valence. So the formula for glycine passes the second senior rule too. Finally, glycine contains 10 atoms. That's 2 carbons plus 5 hydrogens plus 1 nitrogen plus 2 oxygens. So if we call that total number of atoms n, then the third senior rule states that the sum of the valences needs to be greater than or equal to twice n minus 1. So if n is 10, then 2n minus 1 is 19, and the sum of the valences, that's 20, is greater than equal to that total. So the formula for glycine now also passes the third of the senior rules, and as it's passed all of them, we can accept it as a valid formula. Any formulae that don't pass all these rules would be deemed invalid and will be dropped off our list of possible assignments to any peak in our spectrum. Any of the formulae that have by this point passed both the Lewis and senior rules would then be carried over into the next stage. For this next stage, Kind and Fiehn proposed checking any potential formulae against a set of 3 rules that they developed themselves. In order to develop their rules, Kind and Fiehn reviewed 2 huge commercial databases from DNP and Wiley containing standard mass spectra of large numbers of small molecules that have been either synthesized in pharmaceutical research or have been found to be naturally occurring. And they did this to understand how the formula of the molecules in these databases could be grouped. And then from this information they derived 3 rules against which you can test your formulae. The first of these rules is what Kind and Fiehn refer to as their general stoichiometry check. When they were reviewing the databases, they split the molecules into different mass ranges. So those molecules with less than 500 Daltons, then up to 1,000, 2,000, and finally 3,000 Daltons. For formulae within each one of those mass bands, they identified the maximum number of each common element that was found in any formula within that mass range. The 2 different databases gave different results, and they recommend taking the larger result as the envelope-defining stoichiometry for that band. So for example, for molecules with less than 500 Daltons, they recommend a maximum number of 39 carbons, 72 hydrogens, 20 nitrogens, and so on. Whereas for molecules between 1000 and 2000 Daltons, they recommend a maximum of 156 carbons, 236 hydrogens, 32 nitrogens, etc. So to pass this test, any potential formula needs to fit inside the stoichiometric envelope for the appropriate molecular mass range. The second Kind and Fiehn rule are the atomic ratio checks. Again, having reviewed the contents of the DNP and Wiley libraries, they found that the ratios of different elements were also constrained within distributions. So for most molecules, the number of hydrogens divided by the number of carbons, that's the hydrogen to carbon ratio, fell somewhere in the range of 0.2 to 3.1. Although for some unusual molecules, you'd have to look in as wide a range as 0.1 up to 9. But for most of the compounds you'd expect to find on a regular basis, you can easily test to see whether the element to carbon ratio fits within one of these ranges. And providing it does, then it's deemed to have passed this test too. For their final rule, Kind and Fiehn looked at the possible stoichiometric ranges for compounds containing multiple heteroatoms at the same time. So, for example, they found that if a molecule contains more than one nitrogen, oxygen, phosphorus, and sulfur atom, then you would expect it to contain fewer than 10 nitrogens, fewer than 20 oxygens, fewer than 4 phosphorus atoms, and fewer than 3 sulfurs. And any formula that exceeds those rules should either be discarded or at least flagged for specific attention. As you can see from the table, they also produce similar rules for other combinations of heteroatoms. For example, more than 3 nitrogen, oxygen, or phosphorus, or more than 1 oxygen, phosphorus, and sulfur, etc. The cyclothiazomycin structure shown on the right here is one of the molecules at the extreme ends of one of these rules, with a comparatively very large number of heteroatoms for the size of the molecule. So to recap, for every formula proposed by the Dromey Foyster algorithm for any given peak, you should keep only those formulae that pass the Lewis rule, the 3 senior rules, and that fit within the 3 sets of Kind and Fiehn limits. And this process should narrow down your initially long list of possible formulae down to a much smaller, more tractable subset of plausible formulae. And then we'll look at an example of this in a few slides' time. But before we get to that, let's just look at the last stage of our 3-stage process. So having initially developed a long list of possible formulae using the Dromey Foyster algorithm, we've then used some heuristic rules to narrow down that list of formulae to a smaller subset, and then the final stage is to use information about the isotopic distribution in the spectrum to try to identify the most likely assignment for any peak. This process then involves generating the theoretical isotopic distribution for each formula that is still in the list, and then comparing those isotopic distributions to the peaks that we can see in the actual spectrum. In this figure, you can see a comparison of the theoretical isotopic distribution for a particular fragment of a protein, that's the green dots, superimposed over a mass spectral section that could contain that fragment ion. When calculating the theoretical isotopic distribution of an ion, it's important to consider the resolution of the spectrum at the appropriate mass-to-charge ratio. So if we consider the isotopic distribution of the nerve agent Vx, if we were analysing that on a low-performance mass spectrometer with a resolution of only 1000, then we'd only be able to detect up to 4 different isotopolog peaks. However, if we were using a much higher performance time-of-flight mass spectrometer with a resolution, say, of 50,000, then in the A+2 peak we'd see that now begin to split into 2 different detectable isotopolog peaks. Because the peak corresponding to the structure containing one 34S isotope is detectably different in mass at that resolution from all the other A+2 isotopologs. And if we were to analyse Vx on an even higher performance mass analyzer, such as an Orbitrap or FTICR instrument, at a resolving power of 500,000, Then we'd be able to resolve all of the isotopic Fiehn structure in the A+2 peak. So we've gone from only having one detectable peak in the A+2 range up to 1, 2, 3, 4, 5, 6 peaks. And this potentially gives us many more possibilities for confirming proposed formulae. So hopefully this makes it clear why increasing the resolving power not only lets you detect more components in your spectrum, but also lets you have more confidence in the assignments that you've tried to apply to those peaks, with your ability to try to fit the isotopic Fiehn structure. It is important to consider the signal-to-noise ratio though. So if we analysed Vx on this last instrument, but where the Vx signal was relatively weak, the A+2 ions may have an intensity so low that they wouldn't be detected, or where their position or relative intensity would be greatly affected by the noise. And under those circumstances, we would obviously be much less confident in our ability to correctly assign a formula to that monoisotopic peak. So if you want to be able to confidently assign peaks in mass spectra, this tells you that you need high mass accuracy, high resolution, and a sufficiently high signal-to-noise ratio in order to be able to confidently assign any unknown peaks, unless that is you have other evidence suggesting the presence of particular components in your sample. For a molecule as dangerous as Vx, it would be common to use more than one method to confirm its presence in a sample. After all, even if the formula proposed by the accurate mass methods is correct, it's still only the empirical formula and it tells you nothing about the molecular structure. So taking Vx as an example, you'd probably also use a chromatographic method before the mass spectrometer, and this would allow you to check that the retention time of the component that had the right accurate mass to be Vx also matched the retention time of a Vx standard. And then, on top of that, you'd probably also use some tandem mass spectrometry method to confirm that this ion, with the right accurate mass to potentially be Vx, also fragments to produce the characteristic fragments seen from a Vx standard. And it's this combination of retention time, accurate mass, and matching tandem mass spectrometry fragments that provides the gold standard for really confident assignments. But in other applications, you might be using this accurate mass method at a much earlier stage, say to provide clues about what the components in your sample might be. And under those circumstances, you may just be able to use the accurate mass to propose a potential assignment to a given peak at a high enough level of confidence to help you develop the next stage of the project or assay. Alternatively, you might be using the accurate mass method to assign peaks in samples that have such a large number of components that you would never be able to afford to purchase or synthesize standards for all of them. And under those circumstances, therefore, you can only rely on the empirical formula proposed by the accurate mass. In situations like this, the quality of the isotopic match is therefore key to giving you confidence in the empirical formula that you're proposing. In this example, we're going to look at 1 out of more than 6,000 assignments in an environmental water sample. Let's consider the most intense peak in this spectrum, which we've assigned with the ionic formula C18H21O9, and as it's a negative ion, it has an extra electron, hence the E1. Down at the bottom here, I'm showing a zoomed-in portion of the main spectrum, which shows the most intense peak and the region of the spectrum within which its isotopic distribution could be found. The middle spectrum shows the theoretical isotopic distribution for a negative ion with the formula C18H21O9 at the correct resolution for this mass-to-charge ratio in this spectrum. In the very top row, I've zoomed in even further to show the isotopic peak regions in more detail. In each one of these views, the spectrum is shown in red, and the isotopic model peaks are superimposed on that in black. This first view shows the monoisotopic peak, the middle view shows the A+1 peak, and then this third view shows the region including the A+2 peaks. So for this assignment, we can match all of the theoretical isotopic peaks to peaks in the spectrum, and that means we can be quite confident that this assignment is correct. But of course, if we want to be able to apply this approach to large numbers of peaks, then we're going to need to be able to solve two problems. Firstly, we need to find a way of being able to create theoretical isotopic distributions with the correct resolution. And then secondly, we need to find some objective way of measuring how closely a theoretical isotopic distribution matches with peaks we find in the spectrum, Let's look at the first of these problems. So how can we actually calculate the isotopic distribution for possible formulae at the correct resolution? In an earlier video, we looked at simple methods to produce isotopic distributions, using the binomial approach for single element clusters, and then the slightly more complex grid method for small molecules. But the trouble is that although these techniques are a good basic introduction to producing isotopic distributions, they only give you nominal mass peak intensities, and they don't consider the resolution or provide any isotopic Fiehn structure. So we can't use them for this task of accurate mass assignment, and so we're going to have to use more advanced methods. When you need to be able to produce isotopic distributions that can realistically match both the peak shape and the visible isotopic Fiehn structure in a real spectrum, there are three main classes of these more advanced isotopic distribution calculation methods you can use. The first of these is the multinomial approach, which is essentially an extension of the binomial method we covered in the earlier video, but in this case extended to allow any number of elements and their isotopes to be calculated. This method was pioneered by a scientist called Jurgi, so these approaches are often called Jurgi methods. There's a second class based on Monte Carlo methods, and a final class based on a Fourier transform type calculation. The first of these Fourier transform type calculations which was published was called the Mercury algorithm. Unfortunately, we can't cover all of these different isotopic distribution calculation methods in this session. In fact, they'd have to be an entire session or maybe 3 sessions in themselves. But there is an excellent summary of them written by Alan Rockwood and Magnus Palmblad in the chapter on isotopic distributions in this book. But however they're calculated, all of the potential ways of calculating isotopic distributions with realistic peak shapes and resolutions are far too complex to be realistically attempted by hand, so they're always undertaken by software. Many mass spectrometry packages provided with instruments will include these type of calculators, but there are also some excellent ones available for free on the internet. One of the most commonly used ones is the ENVIPAT website, which is provided by the Swiss Federal Institute of Aquatic Science and Technology. It calculates the isotopic distributions using a version of the multinomial approach, and the algorithm itself was published in Analytical Chemistry in 2015. So I've provided a link to that paper here on the slide. Usefully, this website also lets you download the isotopic distributions once you've calculated them, and that's very important for the next stage. In a real sample like this, where you could have 6,000 or more components, and with each one of them having tens of potential formulae proposed for it, and with each one of those having 4 or more isotope peaks to zoom in and check, this clearly isn't something you're going to do by eye. Therefore, even once we've generated the isotopic distribution, we need to find some way to calculate a figure of merit for each possible formula to describe how closely that theoretical distribution matches the peaks we can see in the actual spectrum. There are many ways such a calculation could be done, but the way I do it is to generate the isotopic distribution at the appropriate resolution for each potential formula scaled to match the spectral intensity. The next step is to take each isotopic distribution in turn and find the peaks in the mass spectrum that match those in the isotopic distribution. And it's from these pairs of peaks that I can calculate a figure of merit that tells me how closely the two distributions match. Now this formula probably looks a bit daunting, so I'll step through it. What this bit means is that for each peak in the isotopic distribution, I find the absolute intensity difference between the theoretical peak and the matching mass spectral peak, and then I express that relative to whichever peak is the most intense. If the two peaks match in intensity, then the relative intensity difference is 0. But if the two peaks differ hugely in intensity, then the relative intensity difference gets much closer to 1. Then stepping out one stage wider, this bit just means that I'm finding the average relative intensity difference across all the peaks for a given isotopic distribution. And then finally, I subtract that average relative isotopic intensity difference from 1 in order to give me the figure of merit. So if there was a perfect match between the theoretical isotopic distribution and the peaks I could see in the spectrum, then I'd get a figure of merit of 1. And if none of the peaks were found, then this would give a figure of merit of 0. So the closer the FOM is to 1, the better the match is. If you only have a few potential formulae to check, then you could download the isotopic distributions from the NVPAP website, detect the peaks in them, and then apply the process that I've described on this slide manually to test which of these potential assignments best matches the peaks in your actual spectrum. But if you're using some kind of software to do the assignment, then you may well find that that software will include some algorithm for ranking the assignments in the order of how well the peaks in the mass spectrum match each theoretical isotopic distribution. So, for example, in the software I write, you can see the isotopic match factor, which is the figure of merit we calculated on the previous slide, is shown in this column here. So here you can see that out of the 5 formulae that could be matched within 10 ppm to the most intense peak in our complex organic matter spectra, only the top assignment of C18H2109 gets a good isotopic match factor, indicating that it's the only reasonable assignment to this peak. Every piece of software that you use for doing this kind of assignment may use a different method for calculating the closeness between the isotopic distribution it's suggesting and the peaks in the actual spectrum. And some don't even do this isotopic matching at all and simply choose the formula with the smallest mass error. So it's important that if you're using any software that does this kind of assignment, that you understand how it selects whichever formula it's going to apply. So finally, let's look at how the list of proposed formulae that could be assigned to the most intense peak in this complex organic matter spectrum changes as we step through the 3 different stages of our accurate mass assignment process. In the first stage, the Dromey Foyster algorithm would output 25 formulae within 10 ppm of that peak mass. And here I've ranked them in order of the magnitude of their mass error. So if we stopped at this stage, the assignment would be C12, H33, N2, O1, S5. But then a lot of these formulae would be discounted by the heuristic rules that we'd apply in stage 2. So now we've cut down our list to only 5 formulae, and again if we rank them in order of the magnitude of their mass error, the assignment would now change to be C19, H25, O4, S2. But it's only when we fit the isotopic distributions to all these potential assignments that we can finally identify the correct one. And it turns out it wasn't the formula that was closest in mass. In fact, the correct assignment was C18H2109, as this gives by far the closest isotopic fit. But by following our logical process of using the Dromey Foyster algorithm to suggest all possible formulae within a given mass error of our peak of interest, and then cutting down that list to chemically plausible formulae using our heuristic rules, and then finally testing the isotopic distributions of those plausible formulae against the spectrum itself, we've arrived at a fairly confident elemental assignment for our unknown peak. And so this is the process you should be using when you try to assign unknown peaks in your own spectra. As always, thanks for watching this video, and if you've liked what you've seen, then please consider subscribing to my channel, where you'll find all the videos that I make about mass spectrometry or analytical chemistry in general.